Yeah, hello everyone. Welcome back to the tutorial, and I hope that you can all hear and see me clearly. So we are back from the break now, and we are going to dive directly into the second tutorial, which is on modifying ScaleSim to add custom features, which I think goes quite nicely into the direction of one question that has already been asked. Basically how to change the memory system. And that's what we are going to do here in this very small example. And it's also a nice extension of what you have seen already. So in the last tutorial, you could just use ScaleSim and change some configuration parameters by using this pip install command, which I think is really neat. But if you want to change something in the details and the workings, the inner workings of the simulator, you have to clone your own copy onto your PC. And this is what you're going to learn in this second tutorial. So I hope everybody's back now, yeah, let's just start directly. So the objective here is to demonstrate how you can make use of ScaleSim's modular architecture to add features to the simulator. And first we're going to make an introduction on the architectural modification, which is basically our very toy example case study here. Then second, we are going to dig into the modular software architecture of ScaleSim. Then we are going to modify ScaleSim with some changes to the code, and finally just run this toy example here to get some results for the sake of having some nice results, right? Okay, so let's start and dig into the architectural modifications. So what you've learned so far is you've taken a look at the ScaleSim simulator, and you've seen that this is the basic structure that it gives you with ScaleSim in the middle, and you could give it inputs, mainly the workload parameters and the architectural parameters of your case that you want to test. And then as the results, you got to, for instance, the cycle accurate traces of the memory, summarizes of results, for cycles, bandwidth, and utilization. But in a way, this architecture is fixed, right? So you could change some of these architectural parameters using the config file here. This is what is shown here. So for instance, you could change the size of the array. You could change the SRAM size here, but this basic infrastructure with the double buffered memory for the two SRAMs for the inputs and one double buffered memory SRAM for the output, that was fixed. So if you want to simulate another architecture, for instance, another memory hierarchy, what can you do? And in a way, we got you covered because we have this nice modular architecture of ScaleSim v2. So in our case study, what we want to achieve is we want to use a new custom memory hierarchy with a level 1 and level 2 scratchpad memories. So basically plugging in a second level of memories into your overall memory system. So as I already said, your base architecture that we are going to start with is the default architecture of ScaleSim with the buffers for the filter and the input feature map as double buffered memories. And now in this example, what we are going to do is we are going to plug in a second set of buffers into each of these data flow directions here. So basically we have a second set of or level 2 set of buffers for the filter and a level 2 set of buffers for the input feature map. So that's the basic way to go here. And let's just dig into the technical details. Okay, so this is now going to be on your machine. So I hope you can all stay with me on this, and I hope you have like a Mac or a Linux system so that you can easily make use of that. Actually, I've never run it on Windows, so if you run a Windows machine, I think you have to make yourself familiar with that, how to do this. But in general, we are going to set up the environment now, then check out the code. And then after we have done this, we can dig into more details on how we change the code. So let me just share my screen as a total. So I hope you can now see all this here. So basically, first you need Python, and you need a Python version of 3.6 or larger. So I've gone to a folder here called ASPLOS tutorials, and basically if I type in Python -- version, you will see that I'm running Python 2.7. That's not what we want. So we need Python 3, and that's 3.9. So make sure that you have Python 3 installed on your system. And also you will need to run Git, and for the same thing, I'm going to show you that I've Git installed on my system. So that are like the basic two things that you need. And then you can run ScaleSim. So it's actually also very simple. While you're not using the pip install command, you can just directly use these commands in the next slide. So I hope that most of you have already installed these, as this is standard software on your systems. And then you can get your personal copy of ScaleSim v2 for this tutorial. So there are two ways to do this. There's the short version. So I provided a file here with a shell script that you can just run, which clones the GitHub code, goes into the directory and sets everything up for you. So for future reference, you can easily use this neat little example here. But I want to do the long version just for you to actually get used to how to use it. So we're going to do this manually, what is done in the short version here at the top. So the first command that you want to run is your git clone command. So basically you want to get the current version of ScaleSim. So we do this with git clone, and then you go to the GitHub website here of ScaleSim, and then you can copy the code that you want, the link to the code, and insert it into your terminal, and then cloning into the repository. And yeah, so now what you can see here is that we have a copy of the folder lying on our system. So then we want to enter into the copy of the folder, and then you can see that this is basically the copy of the website there. The first thing that you want to do is setting up your virtual environment. So virtual environment is a way to not installing everything system-wide in Python. And so we are going to do this by typing in Python 3-vn for virtual environment, and then a folder name. We are just calling this vn as well. And then you will set up this basic virtual environment where you can install everything into right now. And we activate the virtual environment with the source command vn bin activate. And now your virtual environment is activated. You will see this by the name of the virtual environment printed at the beginning of your shell. I think that should be the case with all shell systems that you use, that your virtual environment prints itself at the beginning. And you will also see one major difference now if we again type Python --version, which was referencing to Python 2 a second ago. It's now referencing to Python 3 because we installed a virtual environment for Python 3 just before what you can see here. So that's quite neat. And then ScaleSim needs some dependencies, some other libraries that it uses. And for this, we have written a requirements.txt file, which you can see here. So basically, these are our basic libraries that we need. And we can easily install them by just running pip install -r requirements.txt, and then my PC will run a little bit until it's everything installed, and also your PC will probably take a moment for that. But basically this installs all the dependencies for your system, and now you are basically have configured a virtual environment that is able to run ScaleSim. So as you can see here, I just scroll back again. We activated the virtual environment. We installed all the requirements, and this is also written on the slide here. And now we have to install ScaleSim to the virtual environment, and this is done using the setup.py file and the command install. This is also written on the slide. You can see it at the bottom, Python setup.py install, and this installs ScaleSim version 2.0.1, which is the current release to your virtual environment. So now what you will see is that you have some additional folders here, like this act-info folder, which is just there from this build process that we have just undergone. So that's really nice. Now you're set, you can run a ScaleSim simulation on your PC. And yeah, okay, let's continue with the actual tutorial after you have understood how to configure your system. So let's take a look into ScaleSim's modular software architecture. So ScaleSim looks something like this, which is basically an extract from the UML diagram. So we have this ScaleSim.scale base class, and then this basically instantiates your simulator here at the bottom, and this is shown in red. Then we have a compute part, which is shown in green here. And for the sake of the example, I only picked like 3 classes, which are, I think, really clear what they do. So these are the compute classes for the different data flows. And then on the right-hand side, what you see in purple is the memory part. So just to reiterate, we have in red the core setup of the simulator that instantiates at the end this single layer simulator. And this is your simulator of a single layer of your neural network, which is run both on the compute part and the memory part of your simulator. Then in the compute part, we have different components, and the most important components here, of course, are the data flows on your systolic array And those classes are called compute output stationary, compute input stationary, and compute wait stationary. And yeah, these are the systolic arrays with the corresponding data flows inside. And then if you run these, you will also need a memory model, of course, because you need to know when data are going to enter and leave the system. And this is what is shown here in purple. So this is your memory part, and it is separated by read and write components. So on the left-hand side here, you can see the write components, and on the right-hand side, you can see the read components. And then there are two basic classes here, buffers and ports. So your buffer is always this double buffered scratchpad memory representation, and your port is the port that connects to the outside world, to the DRAM, for instance. And the same holds for the read port. And then we have those two modes that Anand already talked at the beginning. So one which just estimates the bandwidth, and one which is the detailed simulation here. So these are the basic components of your of ScaleSim's architecture. And if we want to change our double buffered memory as we intend, we will have to go into this double buffered memory, a double buffered scratchpad memory class, to change our memory hierarchy. And I will show this later in this tutorial. Okay, so let's take a closer look at the double buffered memory. And I just realized I can make the slides full screen for now. So let's take a closer look at this double buffered memory class. So basically, this is this small component here at the left-hand side of your systolic array with your accelerator interface that goes to the outside world, for instance, to the DRAM model that you want to plug into this. And then you have this double buffered memory here with the input feature map SRAM. And that works basically as follows. So you have a class RD buffer, and then you instantiate the input feature map buffer here. And this has a function called service reads. So this function services all the read requests to your buffer. And basically what it does, it is adding latency to the requests for non-stored items from the RD part. So it basically takes a look at which item is already stored in my scratchpad memory and then can compute the latency from that. Or if it is not stored, it has to get the data, fetch the data from outside, from instance for your DRAM. So it wants to get the data from its backing memory. So the memory in the next step in your memory hierarchy. So we have this backing buffer object, which it connects to. And all service reads that cannot be fulfilled with already stored data are sent to this backing buffer object. And in this case, because it directly connects to the outside world, this is your RD port with your input feature map port, which again has a service reads command. And in this case, it adds latency, for instance, from your DRAM model. This is currently only a dummy implementation because we are not shipping ScaleSim with a fixed DRAM model. But if you want to, for instance, use your personal DRAM model, you just have to change this service reads command to add the correct latency. So currently it just adds one clock cycle for the sake of the example here. So this is your basic structure. And in source code, it looks like follows. So we can go into this ScaleSim/memory/double buffered scratchpad memory. And I will just bring this up real quick. Just 1 second. No, that was the wrong. Just a second. Bear with me. So I will share the whole screen again. And now you can see here on the left-hand side your editor. And here you will see that is the ScaleSim v2 folder that I just cloned in my tutorial ASPLOS folder. And then, as you can see here, we have ScaleSim and memory. And then here is the double buffered scratchpad memory file. And this is your double buffered scratchpad memory that I just talked about. And as I tell here on the slides, there are two main things that are relevant right now from what I just told you. You have to instantiate the memory. So this is done here. This is instantiating your memory. And then you also have to connect it to your backing buffer, and probably Zoom is in the way for you as well. I don't know for that. But basically here you are connecting it with the backing buffer, and that's your input feature map port here. So yeah, this is what we just saw, just in code represented again. So here you include this RD buffer object from scalesim.memory.readBuffer, and then you instantiate it. And then here you connect it to the backing buffer system. That's your backing buffer system. And then also you can set the size in bytes. This is the second command here. Where's my mouse? This is the second command here, total size in bytes, which sets the size of your scratchpad memory. Okay, so far, any questions? I'll just wait a second. Just raise your hand if you have questions in the meantime. Otherwise, I'll just continue. Okay, cool. So now it's about modifying ScaleSim, and that's going to be a little bit messy here, but yeah, we have to change some lines of code. It's not super much, but it's some lines of code. So I hope that you can all follow this during this tutorial easily. So in general, what we want to do is that we want to have a level 1 and a level 2 buffer and then connect to the RD port. So this is again shown here in the small figure at the bottom, where you have the input feature map SRAM with the double buffered memory as a level 2 cache, and then, or level 2 scratchpad memory, not cache, and then also level 1 scratchpad memory. So it looks like this now, that from your level 1 buffer, the backing buffer should reference to the level 2 buffer, and then the backing buffer should reference to the RD port. So you're daisy chaining these memory objects here. So how does that look? So we are going to go through all the code changes now, but first I would like to make a short remark. So if you want, you can do this parallel to me on your personal machine and change all the code. But if you don't want to do that and you just want to lay back and listen to me, that's fine, because at the end of this changing all the code, I will provide a link to the changed memory system. So basically, you can also just now take a look at what we changed and then download the changed file at the end. So that will also work for you. In general, what we are going to change is this double buffered scratchpad memory file. And I already opened it in my editor here, and now we are just going to go through all the changes. And I type them in here, and I hope that, yeah, this will work. But before typing them, I think I can make it a little bit more efficient for myself. So if you go to the ScaleSim website, I just want to show this. We have here the tutorial 2, and then here are all the links also to the slides, to the code on GitHub, to the small helper script, and also to the new memory that we are going to change for. So I'm already going to copy this and download this for myself, just to have it as a reference so that I don't make too many typos. Okay, so let me open this here real quick. And this one, and why does it not open? Never know. Ah, now it opens too. That's better, and that's the tutorial 2, and that's the first one. Okay, so this is the original version. So the first thing that we have to do is we have to instantiate the 2 different layers of buffer here. So we have to have a level 1 layer, a level 1 and a level 2. So this is what we have to change here, because here we are instantiating our buffers. So let's get this from this file and put this in here. So yeah, so as I said, you can get the link to this file from the website of the tutorial, but I will also show this at the end. So that's the first one. We have instantiated the new memory now. So now we have to interconnect it to the backing buffer in the scheme that we already discussed. So if I go to my code here, we see that currently still our old input feature met buffer object is directly just connecting into the backing buffer before. So we basically have to change this whole part here by connecting it first to the level 2 memory and then to the backing buffer. So this is something I will again copy from here. And we'll go through the details in a second, but basically you are just daisy chaining it now. So we are instantiating those buffers here as estimate bandwidth mode with the RD buffer estimate function. And then we are setting its parameters. And now you can see from the level 1 buffer, we are interconnecting as the backing buffer object to the level 2 buffer. And we set the total size to some size. And then the level 2 buffer connects to the port. So this is like daisy chaining those 2 buffers and then connecting to the port. And we are also setting the size here. And just for the sake of the example here, we set it to twice the size of the buffer before. And we do the same for the filter buffer. So this is connected to the level 2 buffer, and the level 2 buffer is connected to the filter port here at the back end. So we also have to do this. We also have to do this for the the non-estimation mode. So this is this part here. And as you can see here again, this is instantiating these as actual RD buffers and then interconnecting them by having the level 1 connected to the level 2 buffer and the level 2 buffer connected to the input feature map port. And we are going to do the same here in the else statement here below, because here currently it's still the input feature buffer, the original one that has been instantiated. So oh, that's bad. Hope the alignment works like this. Okay, cool. So let's save that. So now basically we have daisy chained all these buffers in our memory system. So now it's interconnected in terms of the connections, but it's not yet completely interconnected in terms of all the signals and all the process that you have to do. So in a way, you just now have to do search and replace in your code. So what you could do is now you could find all instances of the old buffer name and then just replace it by the new buffer name, but we'll go through all of them individually. So the first one is in the set read buffer prefetch matrix file. So that's here. As you can see here, we are accessing the input feature map buffer and the filter map buffer. So we have to change that. And this is what you can see here. So basically you just have to change it to all the new memory objects that you have. So this is your lines of code here. So this sets all the fetch matrices, and the same goes for the reset signals. So you also have to change all the reset signals to be interconnected correctly. So these are all the reset signals. So this is setting set and reset signals at this point. So then the service reads function is really important, as you already saw at the beginning, because your service read function is the one that connects from the systolic array, from the compute part, to your memory system. And this gives you the latency of your memory. So you have to interconnect it to your memory system. And since the service reads come from the systolic array in our model, you have to connect it to the level 1 buffer. This is what you can see here. We are starting with the input feature map buffer and we are connecting it to the level 1 buffer. So let's take a look at how this looks here. So here in this code, we are in service input feature. Yeah, that's correct. We are in the service input feature map reads, and here it connects to the IF map buffer, but we want to, of course, connect it to the level 1 buffer. And the same holds for the filter. We want to connect also the filter to the level 1 filter buffer. So basically, just think about this again. The input, the service reads are daisy chained via this backing port. So you only have to connect to the first level here because that's your entry point to the memory system at that point. Okay, so now is the next step. We have to change the service memory requests. And at the end of the day, it's looking all very similar to what you have already done. It's just like find and replace here. So again, since this service memory requests are only relevant for the level 1 buffer, so you only have to change the input to your system here. You are going to change this here, and so this is what we are doing here. We are doing the input feature map level 1 and level 2 buffers here, level 1 and level 2. And we have to do the same at the bottom with the prefetch matrices. So here we have to change it to the corresponding level 1 buffer. I should have just copied it all the way, but anyhow, the level 2 one, and again here also the level 1 buffer and the level 2 buffer. So this connects your system for the estimate bandwidth mode and the other for the rest. And here you also can see that you have to, of course, I didn't highlight this on the slide, that's bad. We will do this after the tutorial, but of course you also have to connect to the service reads function, and this connects to your level 1 buffer. And here again, this also connects to your level 1 buffer. And I think that's covered all. Yeah, sorry that I didn't highlight it here, but that's really important to connect to the level 1 buffer here because this is your entry point to your memory system, right? So step 7, you want to generate correct DRAM traces. So the DRAM traces, they are connecting to the level 2 because this is like your latest point in your system. So what you can see here is that you now don't connect to the buffer, but to this level 2 buffer. So let's find the function real quick, which is line will come. Trace matrix, DRAM details, here it is. Input feature DRAM details, I found the function, so it still connects to the input feature map buffer here. So we have to connect this to the level 2 buffer because that's your exiting buffer from your to your memory system. And the same here, you have to change this to your level 2 buffer here as well. And you will do the same for the DRAM filter, which is filter level 2 buffer, and also here level 2 buffer. Okay, so you don't have to change, of course, your output feature map because that is not in a like hierarchical order here. So then we also have to set the other traces, which are down below here, get input feature SRAM trace matrix. So this is also for your level 2 here. And as well as, I'm hoping I'm not making any mistakes right now. Get DRAM, that was wrong. Sorry, I was in the SRAM, I need the DRAM traces, sorry. That's why I was confused. We are talking about DRAM here, of course, because we are connecting to the outside world. So this is the DRAM trace matrix, quite a lot of pattern matching in my head right now, but this should be fine. And also here it's the level 2 one. And then here we also need to change it to the level 2 and the level 2 one. And then we want to print the correct traces, of course. So we have to go to the print DRAM trace function. As you can see, we are nicely arrived at the end of our file. And that's really a neat thing because now we have done all the changes to our memory system. Okay, so just to reiterate here, that was quite a lot of details, but at the end of the day, we have done 3 important things. We have first instantiated 2 levels of memory now. So let's go back at the beginning of the file. We have instantiated 2 levels of memory here. Then we have interconnected it accordingly with the backing buffer system here. And then we needed to interconnect it from 2 sides to the outside world. So one was this service reads function, which connects it from the systolic array to the SRAM system. And then we also had to interconnect it to the DRAM, to the outside world with the port. And this is what we did in the later stuff, where I won't find the function as easily in the editor here, but we can go back to the slides. So this was the part where we only had to interconnect the level 1 system here if we want to enter the memory system seen from the systolic arrays perspective. And then, so this is like your service reads simulation. And then again, to reiterate here, if we want to leave the system, that's going to the traces for the DRAM system that has only been accessed from the level 2 and not the level 1 memory. So this is why we use the level 2 memory here. So that's how you do it. The details are in the slides, as you can see. And now we want to integrate it into our project. And just because I probably made some mistake in typing this here, I of course prepared something as you would usually say in a nice cooking show, right? So we have prepared all the files that you need. So this is the one that I already downloaded to do some copy pasting here, the first one. That is the changed memory system, and we called it double buffer tutorial 2 scratchpad memory. Let's put it into the correct folder. So let's take a look at the terminal now. What you can see here is your basic structure of your ScaleSim project. We want to enter the ScaleSim package here. So you go into ScaleSim, then you have your memory system here, your compute system, some utilities, and your basic simulator setup with everything else. So let's enter the memory system. And as you can see here, here's only the double buffered scratchpad memory.py. And now we want to replace it with the new memory. And I just copy the link here, and you can do the same at home, and you can use wget to get it, and you paste in the URL that you get from the website, and then it will just download for you, and you will see that you now have 2 objects here, the double buffered scratchpad memory.py file and the tutorial2py file. So that's quite nice. But now we wouldn't use it from ScaleSim, right? We still need to integrate it into the simulator. And if you go back in your mind to the first slide, we had this single layer simulator object, which was connecting the compute part and the memory part. So basically, you now have to make the single layer memory object aware of what's going to happen. So let's go back into this. You will find it in the ScaleSim folder, and then we can open it in the editor here real quick. The single layer sim, can you open it please? Yeah, and what you will find here now, and this is also shown on the slide again, and you have the version to replace it for your simulator, but what you will see here is that we include in the original version that we have not modified yet, only the double buffered scratchpad memory. And this is this file here. I hope you can see my highlighting, the double buffered scratchpad memory. We do not include the new version for this. So what we actually want to include is now the double buffered tutorial 2 scratchpad memory. So let's add this double buffered tutorial 2 underscore scratchpad memory. And we want to include this as tutorial 2 memory. That's our name. So now we have made our simulator aware of this new buffer structure that we have. And then the only thing that we also have to replace is where we interconnect it to the memory system. So this was the old name of the memory system. So we just want to interconnect it to the new memory system. So we are commenting this out and making the new memory system. And we called it memory 2, tutorial 2 memory. Okay, so that's it basically. Now you're interconnected and all set. So just so that I avoid any typos or something, I'll just copy the include file, copy link location, double get first, and move the single layer simulator to the old one, singulator pi.old, and move the singulator.1 to single simulator.pi. So now we replaced it. And if we take a look at this, this also should work. This is the old version now, and we want to see the new version. And what you can see here is we included and then we replaced it here. So that's what we expected. Okay, so cool. So now we are all set and we can run some simulations. So let's do some very quick case study here. So I pre-ran everything because it takes like 5 to 10 minutes to run it on my system. So basically what you now have to do, I will show this to you, but you can just directly start running it. So you go back to your base folder here that you still remember. This double buffered memory was there just for the sake of the example. So it should like this for you. And then you can again install your updated version to your simulator. Then you can call directory ScaleSim, and then we have provided a neat little scale.py script for you. So you can just run this by Python scale.py, and this will now start a simulation. And fingers crossed that everything works and I didn't screw up. That looks good so far, so this will take a moment. So what you can see here now, we have an array size of 32 times 32. We are using this convolutional net test CSV file with an output stationary data flow. And yeah, so while this runs in the background, let's first take a look at the results that we will generate. So I printed them here on the slide, and you can easily reproduce those data by just running the 2 versions on your machine. And what you will see is that with the new double buffered memory, what you would expect is that your DRAM pressure is reduced because we gave it like 2 levels of memory, and also we increased the size of the memory. And this is what you can actually see. So what you will see here is that your bandwidth is 4.7 words per cycle and 3.8 words per cycle in the new system. I will just make this larger while my PC still runs. So you can see that your memory pressure has been reduced, and the same holds for the filter from 30 to 1.3. So that's actually really effective what we have done. So, and now just to full disclosure here, we are also now running the simulation, as you can see here, and this will take something like 5 minutes and then just reproduce the results. So that's it for this tutorial. I hope it gave you an idea of how to replace these components in your memory system. And just to reiterate on this. You will find all the required files also on the website. So if it was a little bit too much of information for now, just take your time at home after this, or probably you are at home, it's COVID. So anyways, take your time after the tutorial and then just download these 2 files here, and then you can also just do a diff in your terminal and you will see all the changes. And this should give you a very nice example of how to change or how to use this modular structure to change your memory system. Okay, so with that, I think I finished a little bit too early, but I'm open for any questions. And yeah, I hope this was informative, and I hope also that this already addressed the question that was raised at the beginning by one of you that you had regarding the memory system.
Thanks, Jan. I just had a question regarding the size of the bus width. Is it like easy to change is it like a parameter that you can change the size of the bus, like the granularity that you read the data from different memory hierarchy?
Anand, I think you're the best to answer that.
Yes. It is right. So in when you are reading from this thing SRAM to your array, then your bus size is fixed because you know that you will provide enough SRAM banks for each column, so each row of the thing. But then if you want to go between the SRAMs, you do have different bus sizes, and it is given by I mean, we have not explicitly said it out, but there is a backing buffer bandwidth, right? So backing buffer, this one, the run which Moritz is doing is in estimate bandwidth mode. So it has a backing buffer default bandwidth, but in user bandwidth mode, you will have a backing buffer bandwidth over here, which is basically the bus size in number of words. So let's say if you used in, so Moritz, can you go to else?
Yeah, sure,
line
sorry.
100 and line 110. So here you can specify the bus width between your 2 memories. And then obviously on the top, you can provide the bus width of the DRAM from the config file itself. Does that answer your question?
Yeah, thank you. And another question is how can we keep track of how much of this reading from DRAM is basically overlapped with the computation? What is the metric to see how much is
how much it is hidden? Okay, that's a very interesting question. So the way we do it is this. So there are a few conventions which ScaleSim uses. So computation always starts from 0, right? Now, if whatever access you do to the DRAM before your computation starts is reported in negative cycles, so that you can easily figure out that, oh, looking at the traces, how much data did I bring in the negative cycles? And then the simulator generates in the cycles report file, right? It generates that when did computation stop. And in the details file, you will find that when did the DRAM accesses start and stop. So then you can just remove the overlapping portion, and then whatever excess you have for DRAM accesses. So let's say it says that computations took only 1,000 cycles and your DRAM ended at, let's say, 1,500 cycles. So you can say that, oh, I did 500 cycles. I mean, my DRAM accesses, maybe that was just the right. It took 500 cycles more. To get the exact cycle by cycle metrics, then you have to go and look at the traces to see that what exactly happened. Let's say at some point there was no computation happening. I mean, by no computation, I mean either the pipeline filling or draining was going on, and at that time, if you did any fetching or writing to DRAM or not. So for that level of granularity, right now we do not have anything other than the traces to tell you that in ScaleSim. But if you have very specific requirement, just open a recommendation like enhancement request on a GitHub. I will look through it, and then maybe I will sync up with you again to kind of get sense of what features are you looking for.
Yeah, that's pretty useful, like looking at traces. Like, thank you.
Yeah, you're welcome. Thanks for the question. So we have 5 more minutes, so please feel free to chime in with your thoughts or questions.
I think everybody's just excited how the run will go and whether the numbers fit to what we claim on the slide. So let's see. And it does, it's 3.3 and 1.3. So yeah.
So it's interesting that the runtime actually increased, and maybe that is because of the Zoom running on the CPU.
Yeah, it's now taking 6 minutes, but yeah. Okay, cool. So I hope that was informative to all of you. So let me just go back to sharing the slides. So the next tutorial will be given by Anand again, and it's going to be about building larger simulators. And I know that's quite a lot of work that you invested. So I think that's really worth taking a look at. And I think we can stop the recording now.
Okay.